All right. Okay, we can get started. So welcome everybody to this new world of online teaching. Now, I was online before, so the whole recording process is not necessarily news to me. What is news to me is losing the face-to-face and in-person contact. And I have to say that I was never all that much enjoying online teaching per se in itself. I was just recording my lecture so that it's of service. And I'm gonna miss, and I'm grieving a little the loss of teaching in person, but we gotta do what we gotta do. So we're gonna try the best we can. Do let me know. So I'm gonna actually send later on just as a quick survey of how you're doing and what are the potential difficulties that you're experiencing in this process. We lost basically 2 classes before the spring break, and I decided not to record them and post them as some sort of a homework over these past 2 weeks because there was just a lot going on. So I figured that I should leave the time to everybody to get settled into the new routine. So I hope you have managed to do that. If you haven't, please let me know. If you're facing anything else that might be impeding your ability to study, also let me know. We're all in certain way, we are all basically facing issues, and our all individual issues differ. So it is what it is. Right now, my kids are not around, but you can actually in the future expect that there will be some toddlers flying into frame, and sometimes I can't do much about that, so we're just gonna leave it as is and work with it. All right, so I'm going to then today continue with the lecture that I wanted to post, but decided not to. So a couple of more updates. Is the following. So the exam is still, I have one person that didn't take the exam because of health issues that week when we were taking. So we're going to figure that out this week, and then I'm going to post the results once that exam is taken. You can imagine that taking exam is going to be something that we'll have to figure out actually as we go. Because this new online world has slightly different rules because we can't be on campus. So stay tuned for the results of your exam. All right, so what we're gonna do today, and today there will be the homework posted that is related to the material taught today. Min, can you quickly unmute yourself? So Min is going to send you some pointers. You will essentially have to either type up or scan your homework if you write it on a piece of paper. Min is using software on her smartphone to scan, and she can make some suggestions of what to do. But basically, taking just a picture of your homework is not the best quality for grading. But there are these pretty good tools these days on our smartphones that take a little better version of the scanner. I mean, do you have a comment? What's the name of the software?
Let me check. You are
so you can just send it to everybody as a suggestion, but that's just one suggestion. My point is that you might want to take a little better care in how you take picture of the written material, because now there's no paper. We have to grade everything as a PDF. So that's just a small request. So Min, if you can send, together when we put together homework today, then together with that, make some suggestions. Okay. Yeah. So I will start a lecture today on the PorousMedia, and then I will post both video and the lecture after this. So let's get going. We're going to actually today, let me just move the controls down. we are going to apply what we have learned in microscopic momentum transport to porous media in a relatively simple way, but I still think it's going to be fun. So before we head into that, we actually have to figure out what rocks and permeability are. So if you look at the thin sections that are shown on this picture, there's a limestone, so basically thin sections are done with epoxy. So epoxy, which is blue, is injected into the pore space, so you can see pretty complex pore spaces inside limestone, and the rock is the rest. And then there's a sandstone, similar thing here. The grains are typically a little better behaved, if you will, and more rounded in sandstone reservoirs than they are in limestone. Limestone is characterized with a lot of microporosity that is created in different ways. Sometimes it's dissolution, sometimes it's little critters that have been caught inside a rock. So in either way, we see pretty complex cross sections. Now, what we have learned so far is what the flow looks like through tubes or some sort of constant cross-section objects. So we had a thin slit that we were solving the flow for, and we had a circular tube cross-section in annulus. And you'd be a little hard-pressed to see an annulus around here. Maybe we can actually try and search. This is pretty circular if the flow was actually going in and out. So we will see that we will actually make certain adjustments and simplifications to represent how does flow actually flow through the rock. But let me just further define things. You probably know this from some sort of introduction to petroleum engineering lecture, or you possibly know it from the petrophysics. I'm not sure if you've taken it, so I'm just going to go over basic concepts. So here we have a depiction of grains of the rock. This is a simple depiction, and then this is a slightly different version. So dark is the grains, and pores are in white. This is just one cross section. We typically have three-dimensional objects. Now, what we define as porosity is the volume of these pores or voids divided by the entire bulk volume. So that's typically a fraction, or it could be expressed as a percentage. So I could also multiply this with 100%. So my effective porosity is typically the one that I can actually get into, and that's basically what epoxy does. So when we see a thin section, then we will see where epoxy was able to enter, and those are the pore spaces that belong to effective porosity. Now, rock might have more porosity than that, it's just we can't always reach it. Now, porosity, when we say porosity, we typically look at the total pore volume divided by bulk volume, and that's if we measure it in some sort of scanning way. So we could do X-ray tomography or something of that sort to estimate porosity. However, when we measure it in the lab, we typically, or with a thin section, we're looking at the effective porosity. That's the one that we can actually, that is open to flow of whatever gas or liquid that is entering the pore spaces. These are some common rock types, the range of porosities. If you have unconsolidated, so packings of sand, silt, clay, and gravel, then there's a different range, but ranges are typically larger than 20% in unconsolidated rocks and less than 70%. This is basically 70% you get even if you have clay suspensions that have some other forces at play and not just necessarily gravity settling. Now in consolidated rocks, there's an overgrowth or cement on top of the grains that is keeping them together and also reducing porosity. So consequently, you're going to see much lower porosities, typically down to 5%. This is not or even down to 0. Those are not necessarily reservoirs. Crystalline rocks are rarely reservoirs. So I have a voice amplifier, but that voice amplifier often starts interfering with my computer in some strange trays, and sometimes when I move, so I'm going to have to quickly deal with that. This is one of those learnings. Okay, let's put you on the floor, shall we? Okay. Can't be too far away from me because it's still attached to my face as a microphone. All right. And then we see some complex rocks that are especially of interest right now, such as shale, that have porosities that are much below 10%, which is what we see in sandstones. And those are consequently difficult to explore. Now, this is scanning electron micrograph that actually gives you a little more texture than a thin section might. So you can see some crystals, you can see some clays hanging off the bigger grains here in rough surfaces. Some pores are somewhere in between, and what you see here in section is something that we refer to as a pore throat. So this is a tight pore space in between different grains, and it's the pore throats. So basically there is a part that is here ahead of this in space closer to me, which is sort of a pore or a larger opening. So pores, we often call all of the pore space pores, but we can also talk about pore bodies, which are larger openings or pores, and throats or pore throats, which are the tighter spaces. And those are these tightest points in between grains. They're the ones that actually restrict fluid flow considerably, and they're the ones that reduce the ability of rock to transmit fluid or any kind of other transport that is going through the pore space. So in a sandstone, this porosity is mainly in between these larger particles, and sometimes it's reduced by clay in the pore space. So sandstones is what we're going to kind of think of in the simplified world of rocks that we analyze in petrophysics. You're going to learn much more. This is just a slide with definitions for your reference, which is basically what I already all mentioned. Now, here's a 3D visualization of grains. This is again simplification, assuming that I have a packing of spheres, which is a good model for soils. It's also a good model for unconsolidated reservoirs, for instance, in Gulf of Mexico. So here's a representation of one of these throats. So I have here 3 grains, I apologize. And in between those 3 grains, those are 3 grains that are in very close contact. I have more of them around. I just removed all the others, and you can see one of these throats. So basically passing through something like this. Now it's a shape that is somewhat triangular, though not quite. It's a weird type of triangle. It's the pore space that is left between, in this cross section, between 3 circles, when you think about it. Now, before I head into that throat, I actually have a wider pore space. There's a pore here, and then there's that throat, and then there's a pore behind it, which is more open. So basically you have what we call a divergent converging. I first converge to a tighter pore space, and then I diverge from that. So I have a converging, diverging geometry. Now, this is a larger packing of spheres, so this is just another view of a larger packing where I extracted one of those 3 spheres from. This is another part. This is basically center of one sphere, center of the next closest sphere, 3rd, 4th. So this is 4 close spheres in contact, and I have cut out, so these 4 centers of the spheres, they form a tetrahedron. And I have cut out everything else. So basically you can see one of these throats here on the cross section, and then one here on the back. So every side of the tetrahedron has a throat, and inside I have a pore. So this is this pore throat view of the pore space. Now, this is another word. So if I basically place, I can put a sphere inside that basically shows my pore and connect all of these pores and throats. In this graph, this is how I get this graph. This graph shows me, so this is, let's look at here. This is one pore. This is second pore. This is this middle of the pore space, the opening. And there's a tube in between them. So this is my representation of a throat. It's a simplified representation. So I can have a simplified representation of a tube going in between. So I have a bunch of interconnected tubes. And this is a conceptual network of pores and throats. And this is where our knowledge of how things flow through tubes actually can come in handy, and we're gonna work with that. So here's just, I'm gonna guide you visually just through how some pore spaces look like in 3D. This happens to be something that I study a lot because I take X-ray and microtomography images of pore spaces. This one, I'm starting with a very simple one. This is a model of hexagonal sphere packing. When you get to petrophysics, this is going to be one of the common models that is analytically analyzed. And here, what's simple about it and easy to analyze is that I have a bunch of spheres that are in a regular arrangement. You can see that regular arrangement on top. So I have pores. All pores in between look the same, and all throats look the same. And this is so-called medial axis, or a skeleton of the space. This was done in digital space. This is why it's voxelized, or pixelized rather. You can see how these pores and throats connect. So you have this purple denotes where these pores are, or connections right here. And these other lines denotes where throats connect them. So this is how interconnectivity of this pore space. Another more complicated example is a cross-section of Berea sandstone. So here is basically where we have a Berea sandstone, and there is a pore spaces that are much more complicated. This is also medial axis. This is basically, so you can see that they're both kind of tortuous and much more complex than the previous case. You could also, with this medial axis, see that some of the pore spaces in this, from this image is about 2.5 millimeter across on all sides. You can see that some of these pore spaces are actually disconnected from the rest. So this is this effective porosity would be the connected part, and disconnected would be this disconnected piece. Okay. And these are some of the shortest paths as you're flying across a small sample of a Berea. So you can ignore these graphs other than just understanding. What I want you to understand is that average shortest path, so basically if I start from one face going to another, average shortest path is about 1.9 times, or even 1.8 to 1.9 times the aerial distance. So nothing is straight. I basically have to take twice the time to reach to the other side. So this is, we're going to just briefly stop and check in. Does anybody have any questions? If you do, unmute yourself, make yourself known. Everybody still okay? Okay, I'm moving on. Just going to also briefly check that I didn't get some emails. So far, good. No emails from the class. Okay, so I'm going to move on. So the second, what we really care about in rocks from the petroleum engineering perspective is how much of fluids are down there, and porosity gives me storage capacity for fluids. The second question is, how fast can I actually flow? How fast can I get it out? And that question we typically quantify with permeability. Now, permeability, we're going to define Darcy in a moment, is measured in Darcy or millidarcy. It's a capacity of rock to transmit fluid. Now, it's a function of these open pore spaces as well as how they interconnect. And it depends on certain properties, or we relate it to the properties of rocks, such as grain sizes, how well are they sorted. This is something that you probably talked about in sedimentary rocks. Are there clays within the rock that might, or any kind of influence of diagenesis, such as dissolution or cementation, that affect the ability to flow through the pore spaces? what happened here? All right. Okay. Any questions? Okay. Now, what we typically, how we conceptualize permeability is through Darcy's law or Darcy's model. It's really a model. It was an experiment that was performed to design filtered water in city of Dijon in 1856. Now, what Darcy measured is he put a sand packing, and basically he measured pressure by the height in a tube at the inlet and outlet. So he knew what is the pressure or potential difference between the 2 points. And he could also measure how much flow is coming in and coming out. So he knew what is essentially the volumetric flux going through in meters cubed per second. Now, what he then realized is that when he plots the pressure gradient, or just this pressure head, so this is basically what we were referring to as minus delta P over L, if you remember from formulas. This flux, and this should be upper, I typically use uppercase Q for permeability, so this should be uppercase, is proportional. So basically the two are proportional, the flux and the pressure head. And he basically fitted the data, and it fitted beautifully to a linear model. Now, he also realized that, of course, this flux will depend on the area or cross-sectional area of the sand pack. So you're going to have dependence on that. And then there's what's left is this, he referred to as hydraulic conductivity. Now, he only used water. So basically, it's a permeability that has water incorporated or built in, if you will. And it's measured in meter per second. Now, what we normally break this down into the following. So basically, this is your total pressure or potential, as we call it. So it's the thermodynamic pressure plus rho GH. And when you look at this volumetric flux, it's Ka over rho G delta PL plus rho G. So this is just dividing things by rho G. And if I divide by area, this is a linear flux. It's basically in meters per second. So it's what we often refer to as Darcy velocity. This is my minus delta P over L, Q over mu, K over mu. And it's this K, so mu is my viscosity. In this case, in Darcy's case, he was only flowing water. Now we could flow multiple different things. So we want basically this model to scale out the viscosity of the fluid. And then K, what is left is this geometric measurement. It's a property of a rock only, because by this model, all of the fluid properties are basically here in mu and rho, so they are scaled out. We typically measure it in meters squared. It actually has area, the units of area, and 1 Darcy, which is what we typically use, is 10 to the minus 12 meters squared. This is also 1 micron squared. Okay, so now this was in a straight case. If I had inclined case, I would of course have to take that into part. This again is simply if this is my z direction, if you remember inclined tube, then g sine alpha would be simply the this is z direction component of gravity. Now, and this is basically a vector equation more generally. So this flux is sort of a vector in space. Okay. Now, what we typically refer to as Q is this total flow rate or flux. It's a discharge in volumetric meter cubes per second. Darcy velocity is a linearized discharge, so it's basically divided by A, and sometimes we refer to it as U, or small letter or lowercase letter q. Also, we have to understand that as I'm flowing through the pore spaces, the actual pore spaces on small scale, on pore scale, the linear velocity is actually much faster than what we see as a discharge. Remember that it has to kind of traverse almost twice the length from one side to the other side of the cube. And basically what we refer to as interstitial velocity, V, is this U or Q divided by porosity. And this is again just an estimate of it. Pore scale velocities, they differ widely, and they will of course be nearly zero next to the boundary, and then in the middle of the pore space they will be larger. So there is a range or distribution of velocities. This is just what we take as an averaged value of interstitial velocity. Okay? And you will often refer to, especially in hydrology, this just length h2 minus h1. This is in the head difference divided by L is called hydraulic gradient. But what we look into is this potential, and sometimes labeled uppercase P or also uppercase P. So one thing that we have to understand is that Darcy's law assumes laminar flow in the pore spaces, and this is something that we have worked with so far in Reynolds numbers that are between 1 and 10. So no inertial forces are assumed, and these viscous forces are predominant. It also assumes no slip or zero velocity on the fluid wall. Most of the time, we assume incompressible fluid. If it's compressible, then Darcy's law is way more complex. And viscosity of water is assumed, or that it's technically application to gas flow needs corrections. You're going to talk about that more in the petrophysics course. The model, however, basically assumes the Darcy's model assumes that the permeability is independent from viscosity of the fluid. That in practice is actually not true, and some corrections have to be made to them. Okay. So I'm going to skip those corrections are called Klinkenberg effect, and I'm going to skip them in this. I just wanted to kind of point to it, and you will talk more about it in petrophysics. Now, this permeability is, of course, influenced by pore size, grain distribution, compaction, and how much compaction is present in pore space. I'm sorry. And it's measured on the cores in the lab by injection of fluid with defined properties, and you can measure, just like Darcy's did, the pressure difference. And then you can use this Darcy's law as a model from which you can calculate permeability. In a well, we measure flow and pressure and calculate permeability. That is much harder to do in a well. If well is still open and not cemented, you can actually have a small device that gets to the wellbore wall and tries to inject and see how much intake do you have from the well, and basically then you fet and try to find the permeability. Also pressure transient testing is done, or the permeability is estimated from it. Now here's how permeability for some common soils and rocks happens. So if you have soils like gravel and so forth, then I'm going to have much larger permeabilities. That is here, note that this is the log scale, and this is hydraulic conductivity up here, and this is the permeability here. So basically, you're going to have quite large permeabilities in gravel, and then as you go down, so typical petroleum reservoirs are right here. Okay? So this is from actually a book from Dr. Peters, Advanced Petrophysics. All right. So in order to apply what we know, we're going to conceptualize porous media. And typical models, they assume that when you actually look or analyze a piece of rock, it is representative in some way. And model of tubes, some sort of bundle of tubes, is pretty common. And we're going to, in this course, just refer briefly to this bundle of tubes model, as well as a very simple network model. If you want something more complex, you can do direct imaging and then simulation through. and that's called digital rock petrophysics. That happens to be my research area, but that can take quite a bit of simulation time. It's not easy. So here's a bundle of capillary tubes model that I would like to work through for today. So basically, what we are going to assume is that we have rock space, and I have a bunch of capillaries or tubes that are going across, such as here. And basically, they go from one end to the other. And I'm going to label them briefly. Let me just pull out my pen. Interference. I'm going to turn it off. I'm going to try to speak a little louder. Whoops, and turn off this interference because it's going to be problematic for me to flip over a computer without the interference. All right. Is over here. So basically, what I have here is medium of length L. Okay. And I have the cross-sectional area here. This is the area of the entire side is A. So that is area. So that is cross-sectional area of the rock. And I'm assuming that all of my pore spaces are straight, and they're sort of these tubes that go from one side to the other. At this point, doesn't matter whether I assume that these cross sections are all equal or they have sort of distribution of values. We're just going to pretend that we know what they are. Now, if I focus about, so basically, then by Darcy's law, this is my Darcy velocity, Q, and that is the linearized flux. So uppercase Q, again, is volumetric flux, and A is cross-sectional area, mu is viscosity. So this is my difference in the pressure, and this is my generalized pressure, the one that includes effects of gravity if they're actually important. In horizontal flow, of course, they wouldn't be, but this is just assuming that it's a generalized pressure, and this is my negative, basically, pressure gradient across this length, okay? So this is a model. Now, what we're gonna do is we're gonna recall that in chapter 2.3 in BSL, we had analytical solution for flow in pipe, and this is literally taken as a snapshot from the textbook. This is the average velocity, which took, this is my volumetric flux. This is essentially what Q is. And that volumetric flux was divided by area. This is cross-sectional area, okay? But this is how I get it in general. I have to integrate. This was a circle, so that's why we have a circular, or we have a cylindrical coordinate system. And the flux was basically just integrating velocity V over that circle cross-sectional area. Now, what we get here, so this is basically my area. It basically integrates to R square P, where R is the radius of the tube. Okay? And without going over this again, this is simply a result that we already had. You get that this volumetric flux is R square over 8 times mu. And then you have PR square is the area minus delta P, delta L. Now, if I had this medium where I had a bundle of tubes, then this area actually, so I'm going to denote this area here as AT. So this is basically area of my throat. Okay. And so this is AT. And I'm going to assume that I have number of these throats is NT. So that is number of throats. Okay. Then basically the void spaces that I have, or the area of the void spaces, okay. So void space area or cross-sectional area is simply number of these throats times the area of each throat. And I'm gonna, for now, assume that they're all the same, okay? So what is porosity then? Can you turn on your mics, or somebody turn on the mic to tell me what is porosity based on what I defined so far? Anyone? No one? Hello?
Wouldn't it be NTAT times L over A times L?
Yeah, precisely. Right. So that's basically by volumes. So my porosity, I'm gonna go to switch to a new page actually here. So my feed porosity is cross-sectional, this void space cross-sectional areas. They're all the same. So I multiply them by L to get the volume of my pores, and then I divide by my cross-sectional areas. Oh. Okay. Divide by my area times L, so this is so that's basically void space volume, which is NT cylindrical tubes, divided by my entire volume, so bulk volume. So when I think about the flux through all of these tubes, okay, my flux on one end is flux through NT of these tubes that actually have this. So I'm just going to write that down. R squared over 8 mu times R squared P and minus delta P over L. So this is total flux. This is me and my pen again. Just a moment to erase that. Okay. Okay. So this is my total flux through all of the tubes. So that's flux through all tubes. And I'll compare that. So I want to find out what is my permeability in this. What would be the permeability of the rock in this model? So essentially, I'm going to compare that to Darcy's law. Darcy's law. And by Darcy's law, my total flux should be K over mu, also times area, okay, and times minus delta P over L. So I'm just going to make these things, so this is my Q total. I'm going to make these things equal and then compare them, okay? So essentially, I see that K over mu A minus delta P over L is equal to, I'm going to call this AT, NT AT, and then R squared over 8 mu, and also minus delta P over L. So now I'm just going to get rid of things that are equal on both sides. So this can go away. What else can go away? Mu can go away. Okay, so I can divide by A, and I'm going to get that K is NT AT over A times R squared over 8. And then I can recognize that this is what? Anybody can somebody? Hint, hint. What is this? Porosity. So my K, based on this model, is R squared phi over 8. So this is permeability of bundle of tubes. Okay, so what we can see, what is very specific, is porosity is something that we measure in the lab. We have helium porosimeter, so we can measure. R square is what? R is this radius of the tube. It is sort of this, what is R? It's sort of conceptually this average radius of a tube. So technically, I could look at the thin section and try to estimate what those radii will be. Of course, I actually have a range of those, so I would have to integrate over a number of values, but this is a very simplified model. So if I had some sort of average idea for this radius, then I'm going to be able to estimate, at least in the ballpark, what the permeability of the medium is. One thing that is for certain, this radius, if I think about when we were looking at the geometry, which is what the idea was about looking at them. So if I look at these spheres, I can see that basically if I want to take a radius of a sphere that fits in between these three, that can give me, so if I had a sphere packing of equal spheres, I can basically relate what an average is, or the tightest throat is in between these three spheres. So it's definitely correlated. It's a fraction of the radius of the grains. So if I have some idea about the grain sizes, then basically what this tells me is that my permeability scales as square of the grain size as well, because there's a sum factor here, and then porosity. So I'm roughly proportional to the porosity and the grain size square. This is something that is important to conceptually carry, even if this is not a perfect model. This is something important to carry sort of as a conceptual framework in your brain. All right, this is essentially, we're gonna stop. I'm gonna stop sharing the screen. Everybody's still there? We got a couple of more people. So I am going to basically stop the recording here and post this as a video, and I'm also going to post the slides that I just completed in class, and I am going to open for a couple of questions if you have any. Actually, I'm not going to stop the recording until you stop, until I see whether you have questions. Hello, any questions? No one? Oh, there are some chats. So there is a question. Yeah, my mic is being weird. I apologize for that. That is because I actually have a voice amplifier that I thought would be important for properly recording when I'm at home. This might actually not necessarily be a good idea, so I'm going to have to play with that. We will see when I record the video what is the quality of this last portion when I turned off the mic. I might also need to figure out where to get. So this is probably a good thing when I'm much more away from my computer than I am. Here, when I'm close to the computer, it interferes with it. So it's hard for me if I'm sitting to actually not to interfere. So I'm going to have to play with that. That's on my to-do list. Now, I couldn't hear you. So this I don't know. So I'll have to, again, I will have to review this recording and see what is the best setting for me to figure out. Quizzes, this is a good question. So I'm probably going to do quizzes online now and through Canvas. Not a lot of them though. But that also depends on type of the feedback that I get based on this lecture. It's hard for me to gauge who is paying attention, who is not, when you are so far away. So I might need to institute much more quizzes than I normally do, simply to see whether you all are paying attention. So that's something too. And you can also now turn on your mic and ask questions in person, or if you want to keep it private, I can definitely answer questions from chat. Any other questions about the material? Ruben, are you still having a question here? Do you want that to be a private question, or do you want to just turn on your mic and ask? You're good. Okay. All right. So again, I'm going to post this. Let me know how it worked. Try to look at yourself and how you, it's hard, much harder. It's hard to pay attention to a live person in the classroom, let alone do a video or me just talking over slides. So let me know how that worked. And basically we're going to go from there. I might need to kind of maybe figure out some sort of quick polls. If I don't get a lot of answers from the other side, I might figure out the way to poll all of you to just see that you all are paying attention. Okay, and that's just simply because it is harder to pay attention to class going online. All right. Well, this concludes the lecture. I'm going to stay online. If does anybody have any questions right now in terms of office hours? Okay, textbook chapter. There's no textbook chapter on this one. On this one, we will actually have to refer to the lecture notes. So I'm going to post the lecture notes and let me know if that is not enough. A bundle of tubes model is not covered in BSL. This is something that is added because we are in petroleum engineering and we do need to know some simple models of PorousMedia. Okay. There is some more treatment on sphere packs that is in the book that is on friction factors. We're going to get to friction factors later. They're related to turbulent flow and not to laminar flow, which we have dealt with so far. Okay, so I'm going to post the slides and I'm going to post this video just after the lecture. I'm going to stay online. If anybody tells me if you're going to if you need office hours right now. Oh, Joey is asking when are we going to do here midterm grades. So this is something that I addressed at the beginning. There's one person that didn't take the exam with us, and then this entire situation messed with taking that exam. So we're going to figure that out today about when is that exam going to be taken. If I posted your grades and the solution to the midterm, then it's not fair to you if this person hasn't taken the exam yet. So the grades are waiting for everybody to take the exam, and an unfortunate situation that we are in has messed with that process or the timing of the process. Okay. All right. Any more questions? The plan is, so there's the plan to to cover the same material for the rest of the year. That is not going to be possible. Essentially, we are going to lose the week that we lost last week is the week that we lost. The semester is not going to get longer. So that's essentially at least 1 week less. And so we're going to try to cover as much as possible, but it's going to be somewhat shortened. So we're just going to basically go at the normal pace from now on. Yeah. And whatever we manage to cover is what we manage to cover. Any other questions? Okay, so I'm going to then stop the recording. Let me know if you want to stay online for chat of any sorts. Otherwise, I see you on Wednesday at the same time.